Good morning, everybody. How you doing? So the recitation session on Friday I thought was great. I thought it was a great use of time, and I know there's not room for everybody in that classroom, but there's room for more people. There were 7 students who signed up and came, and I think it was a really good use of their time and a really good use of my time. So that's going to be standard from now on. Fridays, sign up, come, recitation. I'll answer your questions, and we'll go where the questions take us. All right, let's get started. Hi, Chris. Hi, Tristan. So today I want to talk about projectile motion. So I don't do this very often, but I think what I want to do is start with a slide. Show you a PowerPoint slide, and just give me a second, and I'm looking for it. And where is my almost there? Clicky click click click. Study guides. Almost there. Opening up PowerPoint. There we go. Okay, so make this smaller. Maybe make this bigger. There we go. So just a reminder that these PowerPoint slides are posted on Sakai for your reference. And it includes pictures and figures that you'll find in your textbook. So not much here that's new compared to what's in the textbook, but it could be a good summary for people who like this type of thing. Okay, so 2D kinematics and projectile motion. And so what we're going to be doing is studying motion that is along a curved path. And I wonder if I can make this disappear. There we go. And projectile motion is really 3-dimensional motion because projectiles move through space in 3 dimensions, but we can always kind of smush out one of the dimensions. Projectile goes up and comes back down. We can smush out one of the dimensions and think of it as 2 dimensions along a plane that's oriented in the direction of motion. Okay. And so we've talked about vectors, vector addition, vector addition, vector addition. There's a nice review of vector addition here. All right, projectile motion. So this is I wonder if I can make this a little bigger and zoom in on this picture right here. So here is a diagram of projectile motion, where a projectile, whatever it is, travels through the air, and at moments of time, these are like frames in a movie, there's a snapshot showing where the projectile is. And so each of these frames are taken like frames in a movie, taken at equal intervals. Okay, and what you're seeing is that at each of these moments in time, there's a vector imposed upon the object, showing the direction and indicating the magnitude of the velocity of the projectile. And that vector, which is purple in this picture, make it even larger, which is purple in this picture, is broken down into its x and y components. And so remember I said the last time the secret of projectile motion, of unraveling the mystery of projectile motion, involves splitting the dimensions apart. So you have an x and a y dimension to your problem, and you can study them separately. Okay? And so that's done down here quite dramatically, where you see the x component of the velocity and the y component of the velocity plotted completely separate from one another. And the things to take away from this are that the x component of velocity is constant. It doesn't change. And that's because there's no forces along the horizontal direction. When you're dealing with projectile motion, you're ignoring air resistance. So the only force acting on the projectile is gravity. All right, so the velocity in the x direction is constant. Initial velocity equals final velocity, and acceleration is 0 in the horizontal direction, the x direction. In the vertical direction, what you have is motion that looks just like free fall. And here the object starts with an upward velocity in the y direction, and then momentarily comes to rest, and then accelerates downward. So here the acceleration, the velocity is not constant in the y direction, and but the acceleration is. The acceleration is negative 9.8 meters per second squared. It's the acceleration due to gravity. So this is a visual representation of the strategy we will employ to solve projectile motion. Hi Holly. Hi William. Yeah, sorry, I didn't start the stream until right at 9:10 today. So I usually start like 5 minutes early, but I got distracted. So this is a visual representation of the strategy we will employ to solve projectile motion problems. And that strategy will be to break it into two parts, a vertical part and a horizontal part, using what we know about resolving vectors into x and y components using trigonometry. Okay, so let's do it, shall we? Let me see if there's any other slides here worth looking at. I'm zooming out. So this shouldn't be surprising to you based on your experience in the real world, but the distance a projectile travels is a function of its trajectory, and its trajectory is a function of the angle of launch and the initial velocity of launch. Okay. Okay, we're getting ahead of ourselves. Okay, so let's do a problem. And let's go to WebAssign and pick a problem to do from the new homework problem set. WebAssign, here we come. All right, open student view. This is what you see. And so homework number 2, 2D kinematics. It's scheduled due this Friday. There's a video vignette for you guys to work through. So these are not, these aren't meant to be challenging from the standpoint of getting the right answer. But they are really, I think they're really good at making you think about the conceptual nature of a problem, in this case projectile motion. So work through the video vignette with this guy who's got an awesome bandana. Tie-dye, let's bring it back to tie-dye. And then you have a number of projectile motion problems. I think I would like to work on number 3. And what I'm going to do is since we're missing um, a period of instruction each week with the Friday recitation in-person meetings, I'm going to start posting additional content um, asynchronously. So I'll create a video and post it for you guys to watch. And in problem 4 in the homework, I think problem 4 is the most challenging problem in this homework problem set. And the strategy you will employ is very similar to the strategy we'll use to solve problem 3, but it's more challenging just algebraically, because what you end up with is a system of equations, 2 equations and 2 unknowns. But once you realize that, it becomes pretty straightforward. All right, but I'm going to do that problem and post it up. So what I would recommend, if you guys really want to learn, before you watch that video of me solving problem 4, you try it. Okay, you attempt it and give it your best shot. And then when you get stuck, or if you get stuck, go to my video and watch the video until you get unstuck, pause it, and see if you can take it the rest of the way. If you get stuck again, watch the video some more. Okay? You do that, and that's like at least 3 times as effective at learning this material and learning to think this way. All right, so again, I'm going to post me working the answer to problem 4 in the homework, my problem 4, not your problem 4, different numbers. But you try the problem first and really give it your best shot, and then watch my video to get unstuck if and when you get stuck. And then keep going and pause the video and keep going until you get stuck again. And then just use the video as a little boost to get you unstuck, okay? All right. Okay, so let's go back here to this problem. All right, so problem 3. A projectile was launched at an angle of 45 degrees from the horizontal. So that means, these words, horizontal, 45 degrees above the horizontal, okay? Like that, that's what that's telling you. Part of this is just interpreting the words on the page. And it lands 77 seconds later at the same height from which it was launched. What's the initial speed? What is the maximum altitude? What is the range? Calculate the displacement from the point of launch to the position on its trajectory at 68 seconds. Okay, so this last one maybe has a little new nugget for us to consider, but that will be last. Okay, so let's get to the whiteboard. And here we go. Oh, not this one, which is a house with the sun, apparently. Okay. All right. So I'm going to employ this same strategy, which I've been repeating, and you're, as new, my kids have started calling anyone who is new or inexperienced at something a noob, because they've been watching too much Minecraft videos. I didn't think that was a new term. I thought noob was around for like 15 years. All right, but you're not all physics noobs. You're physics new. So you have a strategy that you want to employ. So a projectile is launched at an angle of 45 degrees from the horizontal and lands 77 seconds later. Okay, so my strategy, the strategy that I want you to learn and then adapt to suit your needs, is read the problem. Okay. And then once you read the problem, draw yourself a picture. So here we have a projectile, and it's launched at 45 degrees. So I'll label that vector V naught. And this angle is 45 degrees. And it travels a parabolic path, its trajectory, and lands somewhere over here. And we know that the total time is 77 seconds. Okay. And so I drew a picture, and the problem says that it lands at the height it took off from, at the same height from which it was launched. And, you know, those words have physical meaning. Those words tell us that the initial height, y, equals the final height. Okay, so we have a two-dimensional problem here, and as I'm so eager to remind you guys, when you're doing problems with vectors, you got to define positive and negative directions. So I'm going to call up positive y and right positive x. And so here I have two dimensions. Now, let me zoom in here a minute on the initial velocity vector and show you that there's an x component of that initial velocity and there's a y component of that initial velocity. So I could draw it in component form like that. And so when you look at this, graphically what you're seeing is that the total initial velocity vector is the vector sum of its x and y component. And so graphically, the way I show that is tip to tail. I drew these two things tip to tail. See that? V naught x, V naught y. So I'm using subscripts here to denote the components, x or y. Okay, and sorry, I don't know why that keeps. I thought I turned off the sound. What the heck? Okay. So what I'm going to do is, the next step after I draw a picture is, and define positive and negative direction, is to write down my knowns and unknowns. But here I'm going to create two spots on the page, one for x and one for y. Okay, so over here in the x area, I'm going to write down what I know. Well, do I know anything? I know the acceleration. This is projectile motion, so the acceleration in the x direction is 0. Okay. What don't I know? Well, and also I can say that the initial position is x equals 0. I can just define it that way. Okay, I'm going to say it starts at x equals 0 meters. What don't I know? Well, I don't know how far it went. I don't know how fast it's traveling initially, but I do know that however fast it's traveling initially, that's how fast it'll be traveling for the whole time, because acceleration is 0. So the initial velocity in the x is equal to the final velocity in the x. And I don't know time. Okay, over here in the y, I don't know I can define the initial position as 0. Up here, I can say, this projectile starts right there. Oop, I just erased my projectile. Where x and y equals 0. Right there, I can just define that. So the initial position is 0 in the y direction, and the final position is 0. Because the problem tells us the final height is the same as the launch height. What else do I know? Well, I know the acceleration in the y direction equals negative g, which is negative 9.8 meters per second squared. What don't I know? Well, I don't know the initial velocity in the y direction. I don't know the final velocity in the y direction. I don't know how long it's in the air. Okay. So, time out. I'm trying to be methodical here, and I've broken the problem into 2 problems. Horizontal problem, vertical problem. X problem, Y problem. And for each of those problems, I've written down what I do and I don't know. So do you guys remember? So I'm going to keep going. We're going to then... wait, let me see your questions. Holly, I thought t equals 77 seconds. Well, let's take a look. I'm glad you guys are paying attention. So that is something that's given to us in the problem. So we can make that change. And you might remember from last time that I was asking you about what is the glue that binds the dimensions together? It's time. So if we know the time, that's something that goes with the x problem and it goes with the y problem. Yeah, see, I wrote it down up here and then I got distracted. Move that to the known column. Okay. So at this point, I think we've got a pretty complete picture of the knowns and the unknowns. And what I do at this point is, so the next part of the strategy is to try to connect what's known with what's unknown. And we're trying to find the initial speed of the projectile, but that has an x and a y component. So really, what part A is asking us is what's v naught x and v naught y, and then we can put it together. All right. The maximum altitude. That's an intermediate part of the projectile's trajectory. It's the part where it reaches its highest point. And we have some special information about that point that we can use. And then what is its range? That's its horizontal displacement. X final minus x initial, x minus x naught. All right, so what I usually do is I just take a look at my kinematic equations of motion and just try to get a sense for which of these equations is going to help me in this case. And one way to carry that out is just start writing stuff down. Don't get stuck spinning your wheels. Just start writing down physics equations, and that has the way of sort of clarifying the route for you from beginning to end, the path to the solution. So let's try that. So over here, I'm trying to make that a little bigger. I'm going to put that off the top of the page for a second. Okay, so in the x area, let me draw a little dashed line to separate the page. So over here, one of my kinematic equations of motion is x equals x naught plus v naught x times t plus 1/2 ax t squared. And this kinematic equation of motion for the x part of this problem simplifies a great deal, because that whole term is 0, since the acceleration is 0. And then what we get is, well, this equation. So let's take a look here. What don't we know here? Well, we don't know x. And we don't know v naught x. So we have two unknowns. We can't use that. Well, let's go over to the y. Let's take a look at the same equation here in the y direction. Okay. Well, we what don't we know here? Well, we know v and v. We don't know y and y naught, but we do know that y minus y naught is 0, because the initial and the final position are the same. So this equation can simplify to this. And what don't we know here? Well, we don't know the initial velocity. That's it. That's the only thing we don't know in this equation. We don't know the initial velocity, but we know how long it's in the air. So there's a really important lesson here, or conceptual lesson here, and it's that when it comes to how long a projectile is in the air, the thing that matters is the y component of the motion. So if you know that something goes up and comes back down to the same initial height, and you know how long that takes, you're going to be able to solve for the other thing that matters, which is the initial velocity. I mean, this shouldn't be that surprising. If you have a launcher that's pointed straight up, the faster you launch something, the higher it's going to go, and the longer it's going to be in the air. Okay? So, back to here. So let's solve for v naught y. Okay. And let's plug in what we know. Okay, so one of these t's will cancel. Okay, I've got my calculator here. And I get an initial velocity in the y direction of 377.3 meters per second. Okay. So at this point, you may not realize it yet, but we have the piece of information that we need to figure out the initial velocity. We found, so what we just found was not the initial velocity. What we just found is the y component of the initial velocity. But remember, this thing is not just going up and down, it's also going horizontally. Okay? But I'm telling you, we just found the vertical component of the initial velocity, and I'm saying now we can find this. And the reason is because we know the launch angle. They tell us the launch angle is 45 degrees. Okay, so this is not so much a physics problem, but a trigonometry problem. All right. So what I'm saying is, let me redraw what I had up top. We're after this. We're after V naught. But V naught is an x component and the y component. And that angle is 45 degrees. So what we just found is that component. So now we have enough information to solve this triangle completely. We know that V naught is V naught y is V naught sine of 45 degrees. That comes from trigonometry. The sine of 45 degrees is opposite over hypotenuse. Okay, this over that. You just rearrange that equation and you get this. And we know the x component is V naught cosine of 45 degrees. Okay, so let's go over here a little bit more. So let's plug this in down here and solve for V naught. V naught equals V naught y divided by sine of 45 degrees. Okay, so the initial velocity is 533.6 meters per second. And then when you use that to find the initial velocity in the x, what you find is it's 337.3 meters per second. It's exactly the same. Okay, so that shouldn't be too surprising, because why is the x component the same as the y component? And it has to do with, this is a special case. This is a special case where the launch angle is 45 degrees. If you think about 45 degrees, 45 degrees is the angle that's going to split the triangle so that the two sides are exactly the same length. V naught x is equal to Vy. All right. All right. So let's see. Let's go back. Let's check. All right. Let's go back to WebAssign and let's enter this answer. So we found that the speed of the projectile, initial speed, was 533.6. And let's check our work. Good. No mistakes. Okay. So I make mistakes all the time, so it's good to stop and check. As you guys know, 3 weeks in, I make mistakes all the time. So it's good to stop and do a little check of my work. All right, so the next part of the problem is, what is the maximum altitude? Okay, so we could proceed in a number of ways here, but let's be clever. Okay, so this is a projectile that goes up and comes down at the same height. Wish I could draw in the air someday. But it goes up and comes back down at the same height. And we know that the projectile, this whole path takes 77 seconds. Okay. So how long does it take to get to the top? Anybody care to submit a guess. Half of 77, right, Holly? So if it takes 77, it's a parabola. You know, it's a rainbow. And so there's a symmetry. You know, symmetry is a powerful tool in physics. Anytime you have situations where you can observe symmetry, that symmetry is going to help you simplify the situation. So we have a parabolic path that's perfectly symmetric. The initial height is the final height, so the midpoint is exactly halfway between the beginning point and the ending point. So half of 77 is 37, blah, 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 is what we need to know here. Okay. So this is like kind of like a side problem here. It's like how high does it go? Well, in this particular case, what we know is what we have already figured out. We know the initial velocity. We know the rate of acceleration. And we know the time it takes to get to the top. 37 divided by 2 is 38.5 seconds. And we know when you get there, you're momentarily at rest. So if you say you start at 0, how high do you go? So all this is a little side problem. Okay. All right. So let's see. I think that this equation is going to get us there. All right. So we solve for y. We said y naught is 0, so that goes away. And now we just plug in what we know and solve. Okay, so let's do that. 377.3 times 38.5. Holy smokes. That's what I got. I wonder if I made a mistake. I'm going to put it into WebAssign here and just check quite quickly. It's correct. Boy, that projectile goes high. Okay, that's its maximum height. So this is its max height right there. Okay. So let's go over here. So the other thing we wanted to find was its range. So that means we got to come all the way back here to the x. Okay. And now we can finish what we started, because our endeavors to discover what was going on in the y direction has yielded information about the x direction, v naught x. So we've found now that the initial velocity in the x is 377.3 meters per second. So now we can use that to figure out how far it goes. And of course, we said the initial position is 0. So if something's traveling 377.3 meters per second in the horizontal direction for 77 seconds, it travels 29,052 meters. Okay, its horizontal range is 29 kilometers. So let's put that in. and check our work. We're good. Okay, so this, I didn't, I purposefully didn't do this problem before we started today because I wanted my process to be as real as possible. And the real process is not one where you immediately know the path to a solution. The real process is a system. It's a way of approaching the problem that's going to allow you to consistently solve the problem. Okay? And I mean, one thing you'll notice is that process, that system, has errors, and and has dead ends. But if you have that process, you have that system, you're going to be able to catch those problems. And so here we started by looking at what's happening in the x direction, and we reached a dead end. But that wasn't the end of things. I said, well, let's just, to use a term I don't like, put a pin in it, and then let's go look at what's happening in the other dimension. And we uncover more knowledge until eventually we get a piece that will allow us to come back and get unstuck in the x direction. Okay, so this is an important way of thinking. Your thinking should be focused on developing a system, developing a process, a way about approaching these problems. And I think one thing that really frustrates students in physics is there's a complexity that they're not used to. There's the mathematical part, but I think most of you are pretty comfortable with the mathematical part, the algebra, mainly the trigonometry. But there's a complexity, and this complexity is like there's more information than you can like buffer in your mind at one time. There's too many variables, too many moving parts, and I'm telling you, you shouldn't try. Don't try to approach a problem like that. You've got to have a system which involves, systematically approaching the problem, writing down what you know, what you don't know, drawing pictures, writing down formulas, connecting what you know with you don't know. And this is like, you're not trying to attack the whole thing at once, right? You're doing, you're not getting bogged down in the complexity of the problem. All right, so there's one more part to this problem. It says calculate the displacement from the point of launch to the position of its trajectory at 68 seconds. Okay, and so what this involves, let's go over here. So what this involves is it's like a part of this problem where you're like, okay, the projectile is launched, and then at 68 seconds, it's somewhere. Okay, it has an x coordinate and a y coordinate. So it starts at xy equals 0, 0, and it ends somewhere. So this is saying, find this displacement. All right, it's representing it as a vector r. And so r is going to have an x component and a y component. Okay, so this is an image of what you're trying to find here. So it's like take a snapshot, not when it reaches the end of its flight, but 68 seconds in. And where is it? Okay, so you got to figure out what x is at that point. It starts at 0, 377.3 meters per second times 68 seconds. It's 25,656.6 67.4 meters. Okay. So we can figure out how far it is at that point using the same kinematic equations of motion. And what about y? We can use, I didn't include the 1/2 axt squared up there because that term goes to 0 in the x direction. All right, in the y direction, we say it starts from 0, so that term goes away. The initial velocity in a y is 377.3 meters per second. T is 68 seconds. Acceleration is negative 9.8. Times 68 seconds squared. So that is 2,998.8 meters. Okay. So since we started at 0, what we found, the final position is the delta. It's the change in x and the change in y. So our final answer here is the displacement vector from where we started is 25,656.4 I hat plus 2,998.8 j hat meters. And I'll leave it to you to do the last piece here, but it's not so bad. You know, if you have a vector r that looks like that and has an x component and a y component, there's the x component, there's the y component. So the magnitude of r is the hypotenuse of a right triangle. It's going to be the square root of rx squared plus ry squared. Well, let me just do it right now. Make sure I didn't make any mistakes. So I got that, 25,831 meters. Oh, it wants me to put them in using vector notation. All right, so I would put in my answer exactly like I've written it up here. Okay, that's what it wants me to put in. All right, so that's enough for today. So tomorrow we'll meet up for lab at 1:50 and talk a little bit about the activity for the week, which is already posted, ready to go for you if you want to get a head start. Look for an announcement saying that I've posted a video with some extra help, okay? Some extra problem-solving help on projectile motion. All right. I don't see any other questions, so thanks for joining me, and I will see you tomorrow.